very much. Yeah. Yeah.
Hi everyone. Yeah, now I'll be giving a talk on the ongoing project called Future Projection of Atmospheric and Oceanic Impact on Sea Level at Arctic and Near Arctic Coastline, shortly referred to as Future ESLA. Yeah, that's me and Gerard, and we've got other partners like Vera Shinta in China. So we have ICIT in Germany. Yeah. Yeah, so when I talk about the future ESLA, so it's actually a project that seeks to give an insight into the future state of the ocean in the Nordic, Arctic, and the Irish coast. And then basically when you are talking about the Arctic system, the Arctic system is a complex system that involves the ocean, the sea, and the ice. And this system actually interacts with the low and the mid latitude. This interaction plays a prominent role in determining the weather both in the poles and in the tropics. And key among determining factors is what we call AMOC. And when we say AMOC, it simply means Atlantic Mediterranean Ocean circulation. And when you are talking about AMOC is one of the crucial global ocean currents. So, and the role it plays here is that it helps in transporting warm sea surface ocean with ice salinity from the tropics to the pole. And as this moisture is being transported towards the pole, it sinks and cools, and it's being transported southward. And this continuous movement of moisture, both from the poles and from the tropics to the pole, helps in determining regional sea level rise. And basically, so the state of AMOC plays a prominent role in this location. In recent times, so the AMOC has indicated slowdown, and then the state of the AMOC plays a prominent role in the determination of the storm track. So, and when AMOC enhances, so you have a northward movement of the storm track, and when it slows down, that means weakens, so you have a southward movement. And the implication is that when there's a reduction in the transport of warm water towards the pole, so you have a more harsher winter period in the Arctic. So in this project, so we are employing the SIMA 6 model output, and then the variable that is being considered for this project is ZOS. And when I say ZOS, I simply means dynamic sea level rise, or in a more technical term, the sea surface height above geode is the parameter that is being provided for in SIMA 6. Yeah. Yeah, and due to past engagement that I've had, so there has always been a question around dynamic sea level rise and total sea level rise. So in view of that, I just want to give a short, and it brought in this PowerPoint to give an insight into what I mean or what is meant by dynamic sea level rise. Basically, due to global warming, so the sea level rise there's an increase in sea level rise. And this increase is a kind of setting up a global baseline. And the truth about the whole thing is that the global sea is rising, but the distribution of this water mass varies across regions. And this distribution is being influenced by factors, local oceanic factors and atmospheric factors. And these two factors is crucial for regional research, such as future ESLA. And due to the fact that, the component of the oceanic component is being adopted in dynamic sea level rise. And that is why, that is one of the justifications for the adoption of dynamic sea level rise to undertake this project. And when you look at the total component of the sea level rise, so you have the dynamic sea level rise, DSL, you have the steric component, you have the barystatic component and the glacier adjustment component, and the local component. So in this set of research that I will be giving, so it's basically based on the dynamic sea level rise. So having said this, I believe I've been able to provide an insight into the difference between dynamic sea level rise and total sea level rise. Yeah, and this is the historical dynamic sea level rise over the study area. So in this plot, I'm presenting 19 model output from CMAP 6. And then when you look at this model individually, you could see some variability that is being seen. And to actually provide and to reduce this variability, I employed what I call MMM. MMM simply means multimodal assembled mean. And the inference being taken and being given is actually from the multimodal mean. So the state of the study area actually indicate a positive trend, and which is significant at 95%. And before I move to the next slide, there's this assumption in my mind that okay, for every increase in global temperature, there is expected to be a consequential rise in sea level rise. And in view of that, so CMAP 6 actually provides what's called future scenarios under different global warming thresholds. So when I say global warming threshold, I'm referring to SSP 1.26 being 1.5 degree, SSP 2.45 being 2.0 degree, and SSP 5.85 being 3.0 global warming threshold. I'll be using these two terms interwovenly. So when I say global warming threshold, referring to 1.5, 2.0, and 3.0, and when I say SSP 1.26, 2.45, or 5.85, I'm still using the same terminology. Yeah. So quickly, I look at the future state of the seal under the 1.5 global warming threshold. So relatively to the historical run, so an increase is being seen, which is more prominent around the Greenland and the Iceland and Norway. Then further increasing the global warming from 1.5, I omitted the 2.0 because though there's an increment, but the increment is more pronounced between, the difference is more pronounced between 1.5 and 3.0. So really, when you compare the 1.5 global warming threshold and the 3.0 global warming threshold, a further increase is actually being reviewed, which actually justify one of the things that we have in mind that okay, for an increase in the global warming, that we expect a consequential increase in the sea level. And of course, this, just like it is being known that the distribution of water mass varies across regions. So this difference is it varies along regions. So when you see the southern part of the Greenland under the 3.0 global warming seems to be pronounced. So looking at the Norwegian coast too, so you could see a pronounced increase, and in the Iceland too, so you see an increase. So I know one of the things that is still being under investigation is that I expected that okay, even in the Irish coast too, there will be a pronounced pronounced increase too. Then the next plot is to zoom in, bringing in the regionalization factors. Okay, talking about different regions, the Arctic, the Nordic, the island, and the EEE is actually island exclusive economic zone. So to structurally see the contribution of dynamic sea level rise to the state of the ocean there. So when you look at the legend that is being shown, the SSP 1.26, that is the 1.5 global warming, the 2.45, the 2.0, which was omitted in the spatial temporal plot, and the SSP 5.85. Yeah, a closer look at this time series plot actually shows that the dynamic sea level rise contributes significantly to the sea level, to the state of the ocean in the Arctic and in the Nordic, but relatively to islands. So it's not, so the contribution is actually minimal. And one way that one of the thoughts that is in my mind now is that, of course, based on the second plot where I show the different components of the sea level rise, we have the dynamic component and the static component. So perhaps when the static component is being overlaid or combined with the dynamic sea level rise. So the expected change, which we are expecting in the Irish coast, could actually come to view. I must say that this is an ongoing project, so there are more thoughts to the project than what is being presented here. And further analysis that was done in relation to the relationship between AMOC and dynamic sea level rise. Just like in the introduction slide, I made mention of the role that is played by the state of AMOC, its enhancement and slowdown. So never mind the historical plot. So I guess the resolution is quite different from the other. But when you look at this plot that is being displayed here, so we could see that the state of the AMOC seems to have a close relationship with the rise, with dynamic sea level rise in the southern Greenland and in the Nordic coastlines, especially under the 3.0 global warming threshold. Further question that I seek to ask and to provide insight to in future presentation is to actually give an answer to how we projected AMOC under different climate scenario impact regional dynamic sea level rise. And some of those slides are giving a preliminary insight to it, with focus in the Europe and the Arctic. And then how does AMOC variability influence extreme dynamic sea level rise, especially using the threshold 1999 percentile on different time scale, and the collapse of AMOC. So what is expected, or what is likely going to be the expected impact on dynamic sea level rise anomaly across different regions? And the last question is how well does CMAP6 model capture this relationship that is being presented? Yeah, thank you.
Thank you very much.